for the tiniest increment of time that is possible to talk about, 10 to the minus 43 seconds. The temperature was 10 to 32 degrees, and the density downright indescribable. At that instant, there was only one universal force and one type of elementary particle. But it wouldn't last. At the end of this instant, gravity separates itself from the union. At 10 to the minus 35 seconds, the strong nuclear force exits the union as well, and this triggers inflation, the event where the universe instantaneously grew into size, from tinier than an atom to an unknown large size. This expansion and subsequent cooling down to 10 to 27 degrees allows 6 different types of quarks to form. At 10 to minus 12 seconds and 10 to 15 degrees, the weak force and electromagnetism separate, and we have the 4 independent forces we know today. At this point, all 6 types of leptons have formed, including the electron. At 10 to the minus 6 seconds, up and down quarks have formed protons and neutrons. All heavy quarks have decayed. All heavy leptons have decayed. All antimatter has disappeared. And by the time the universe is only 1 second old, protons and neutrons are already getting together to form the lightest atomic nuclei. As we take apart matter down to the smallest scales, we must pass through levels of structure that are only possible because of forces that hold these structures together. The proton and electron, for example, are attracted to each other, and that force of attraction is what holds them together in the atom. But what is it really that causes this attraction? How does the electron know the proton is there? And what draws it towards the proton? How does the electron know not to be attracted to the neutron? The answer is that the electron and the proton each fill the space around them with countless millions of other tiny particles that have only the most ephemeral existence. Because it is electrically neutral, the neutron does not. These particles come into existence only briefly and are gone, only to be replaced by another one thrown out by the parent particle. On this scale, the tiny bit of energy that is needed for the existence can be created out of nothing. But they also must disappear in the briefest instant, because the energy used to create them can only exist for a very brief instant. You can imagine these virtual particles as balls tethered to the parent particle by a rubber band and snapping back to the parent when they disappear. If one or more of them should encroach upon the territory of a virtual particle tethered to another parent particle, they can get entwined and exchanged. Such an exchange is felt by the parent particle as a force. Scientists recognize 4 distinct kinds of force fields, and they all work through the mechanisms described above. You are readily familiar with 2 of these forces: gravity and electromagnetism operate on a scale that we encounter in our everyday life. A third force causes quarks to stick together in protons and neutrons, and a residuum of this force causes protons and neutrons to stick together in the nucleus of atoms. This force is called the strong force, or sometimes the color force. The fourth force causes radioactivity and is called the weak force. The virtual particles that make up these fields and get exchanged in each force are called gauge bosons. And each of the four forces has its own gauge boson. Within limitations, energy and mass can be created out of the nothingness of space-time, but only for a very brief instant. And the more energy and mass these virtual particles have, the shorter must be the time that they can exist before snapping back to the parent. Lighter gauge bosons can exist for a longer time, and these in turn can get further from the parent before they must return. So the range of a force is directly related to the mass of its gauge boson. The photon is a gauge boson for the electromagnetic force, and the graviton is the gauge particle for gravity. Both of these particles are massless, and so the range of these two forces is unlimited. The strong force is much more complex. The charge property responsible for the force between quarks comes in three distinct states. Not just two, like the positive and negative charge states in electromagnetism. So in a loose analogy to the three primary colors, red, green, and blue, the three kinds of charges in a strong force are usually referred to as color charge, and are designated red, green, and blue. Since the theory of electric charge is dubbed quantum electrodynamics, or QED, the name for quark theory has become quantum chromodynamics, or QCD. It is interesting to note that all observed particles are white. Color is never visible. And since the proton and its baryon cousins each have three quarks, the color possessed by the three quarks must be one each of red, green, and blue, which sum to white. And mesons are always a quark and an antiquark pair, containing colors of red, anti-red, or blue, anti-blue, or green, anti-green. Also combinations that equal white. The strong force, of course, must have its own gauge boson, and it turns out that there are 8 of them. 8 different gluons that carry the color force. And unlike the other force carriers, gluons have a color property themselves, and therefore interact with each other. Every time 2 quarks interact and exchange a gluon, they swap colors. Also, because gluons are attracted to each other, it is possible to have a gluon collection, which is referred to as, what else, a glue ball. The interactions that result from the weak force are incredibly short-ranging. They are effective over a distance even smaller than a proton's diameter. And this accurately implies that the weak force gauge particles, called the W and the Z, are immensely heavy. Over distances small enough and at really high energies, the 4 forces are indistinguishable because their respective force particles are also indistinguishable. The standard model of physics combines QCD with QED and the weak force theory. It states that there are 6 quarks and 6 leptons and 12 gauge bosons, as well as their antiparticles. But only the up and down quarks, the electron, and the lightest neutrino are populous today. In this standard model, the entire system of matter and forces except gravity, is encapsulated in a few simple equations and is organized around one core principle known as local gauge symmetry. Amazing. For the tiniest increment of time that is possible to talk about, 10 to the minus 43 seconds, the temperature was 10 to 32 degrees, and the density downright indescribable. At that instant, there was only one universal force and one type of elementary particle. But it wouldn't last. At the end of this instant, gravity separates itself from the union. At 10 to the minus 35 seconds, the strong nuclear force exits the union as well, and this triggers inflation, the event where the universe instantaneously grew into size, from tinier than an atom to an unknown large size. This expansion and subsequent cooling down to 10 to 27 degrees allows 6 different types of quarks to form. At 10 to minus 12 seconds and 10 to 15 degrees, the weak force and electromagnetism separate, and we have the 4 independent forces we know today. At this point, all 6 types of leptons have formed, including the electron. At 10 to the minus 6 seconds, up and down quarks have formed protons and neutrons. All heavy quarks have decayed. All heavy leptons have decayed. All antimatter has disappeared. And by the time the universe is only 1 second old, protons and neutrons are already getting together to form the lightest atomic nuclei. This is how we represent an electron visually. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So we instead represent the properties that allow the electron to interact. The central small dot represents the weak charge of the electron. This charge, entirely separate from electric charge, gives rise to the weak nuclear force. This force causes radioactive decay, and its typical range is much smaller than the diameter of a proton. The larger volume of shifting purple is meant to represent the electric charge of the electron. This charge is the generator of the electromagnetic force, which has infinite range, although the drop-off of strength is pretty dramatic as we move away from the electron. The electromagnetic force is how electrons interact with other electrically charged particles and with magnetic fields. These interactions make the structure of atoms and molecules possible. This gives rise to almost all of the complexity that we see around us. This is how we represent the up quark visually. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So we instead represent the properties that allow the up quark to interact. The central small dot represents the weak charge of the up quark. This charge, entirely separate of electric charge, gives rise to the weak nuclear force. This force causes up quarks and down quarks to swap flavors, and its typical range is much smaller than the diameter of a proton. Surrounding that is the volume depicted as gold for the up quark. This represents the electric charge of the up quark, which has a positive charge of plus 2/3 units. The electric charge is the generator of the electromagnetic force, which has infinite range, although the drop-off in strength is pretty dramatic as we move away from the quark. The larger volume of shifting red, green, and blue is meant to represent the color charge, which generates the strong nuclear force. This is the force that holds quarks together in a proton or neutron. And a residuum of this force holds the proton and neutrons together in the nucleus of an atom. This force is 100 times stronger than the electromagnetic force, but its range is limited to about the size of a proton. This is how we represent the down quark visually. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So, we instead represent the properties that allow the down quark to interact. The central small dot represents the weak charge of the down quark. This charge, entirely separate of electric charge, gives rise to the weak nuclear force. This force causes the down quark to change into an up quark, and its typical range is much smaller than the diameter of a proton. Surrounding that is a volume depicted as purple for the down quark. This represents the electric charge of the down quark, which has a negative charge of 1/3 units. The electric charge is the generator of the electromagnetic force, which has an infinite range, although the drop-off in strength is pretty dramatic as we move away from the quark. The larger volume of shifting red, green, and blue is meant to represent the color charge which generates the strong nuclear force. This is the force that holds quarks together in a proton or neutron, and the residuum of this force holds the protons and neutrons together in the nucleus of atoms. This force is 100 times stronger than the electromagnetic force, but its range is limited to about the size of a proton. This is our depiction of a proton. It is composed of 2 up quarks and 1 down quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of the proton is positive, and so we have given it a gold shell. Note that we can simply add the charges of the individual quarks to get the charge of a proton. The red, green, and blue colors of the quarks represent the color charge which generates the strong nuclear force that holds them together. It comes in 3 different charges, represented here by 3 colors, and for different colors, force is attractive. The mediator of the strong force, the particle that is exchanged in an interaction, is a gluon. We represent gluon exchange as the occasional wispy string between the quarks. As you can see, the gluons have color themselves, and each gluon exchange causes the quark involved to swap color. Although we show quark motion inside the proton as leisurely, they are actually traveling close to the speed of light. Oh, protons taste sour, like vinegar and lemonade. This is our depiction of a neutron. It is composed of 2 down quarks and 1 up quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of a neutron is neutral, so we have given it a silver shell. Note that we can simply add the charges of the individual quarks to give the charge of the neutron. The red, green, and blue colors of the quarks represent the color charge which generates the strong nuclear force that holds them together. It comes in 3 different charges, represented here by 3 colors, and for different colors, the force is attractive. The mediator of the strong force, the particle that is exchanged in an interaction, is a gluon. We represent gluon exchange as the occasional wispy string between the quarks. As you can see, the gluons have color themselves, and each gluon exchange causes the quark involved to swap color. Although we show quark motion inside of the neutron as leisurely, they are actually traveling close to the speed of light. This is how we represent a neutrino. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So we instead represent the property that allows the neutrino to interact. The white area represents the weak charge of the neutrino. This charge, entirely separate of electric charge, gives rise to the weak nuclear force. This force allows the neutrino to interact, but only very weakly, and its typical range is much smaller than the diameter of a proton. Neutrinos are produced when a down quark decays into an up quark and an electron. Conservation laws require that a tiny neutral particle is created in beta decay. And the particle is the neutrino. Well, technically, it's an antineutrino. Because the neutrino only interacts through weak force and negligible gravity, it almost never interacts with other particles on its own. Millions of neutrinos stream through your body every second, totally unnoticed and unnoticeable. Gluons mediate the strong force. They have no mass, no electric charge, and no weak charge. So depicting gluons visually is a real challenge. To begin with, there are 8 of them, and each carries a combination of color charge. Secondly, there are no free gluons. They exist only virtually when 2 quarks interact. Third, since gluons have their own color charge, they generate secondary virtual gluons. These generate other gluons ad infinitum. This means there's such an ongoing storm of these gluons that the whole process is impossibly complicated. But undaunted, we press on. We know that when gluons cause 2 quarks to interact, the quarks swap color. And since color is conserved, the gluon must have at least 2 colors of its own. Next, we know that the strong force mediated by the gluons increases the strength as the quarks get further apart. This means the gluon field is what is called a flux tube, and this leads to a gluon shaped like a string. Putting all these ideas together leads to the depiction you see on the screen. Photons are the gauge bosons, the force carriers for electromagnetism. Whenever charged particles interact, photons are exchanged. They have no mass, no electric charge, no weak charge, no color charge. The epitome of almost nothing at all, and yet here is where it's at. Since they are responsible for all electron and proton interaction, everything we do in our everyday life, from moving a mouse to running in the park, relies on the exchange of photons. They are energy contained in shifting and changing electric and magnetic fields. Like all particles with no rest mass, photons travel at the speed of light. They cannot come to rest. Photons, in the range of visible light, carry just enough energy to excite a single molecule in a photoreceptor cell of your eye. Weak bosons, also called intermediate vector bosons, are the exchange particles for the weak nuclear force. There are 3 of them, called W+, W-, and Z0. They are very massive, each being 80 to 90 times as heavy as a proton. Because they are so heavy, the uncertainty principle allows them only an extremely short range when they act as force carriers. So the weak nuclear force has a range about only 1/100th the diameter of a proton. The W bosons cause quarks to change flavor, while the Z has an effect in an esoteric type of interaction called neutral currents. Gravitons are the as-yet undiscovered force carriers for gravity. Because of the great success of the Standard Model, in describing the other three forces which exchange bosons, it is assumed that gravity has a gauge boson as well. Its properties have been extrapolated. It is a massless, stable, spin equals 2 particle that travels at the speed of light. Gravitons may not be constrained to the dimensions of space and time that we experience. Today we will talk about the mechanism that causes fundamental particles to have mass. If the electron had a different mass, then the orbitals inside atoms would be a different size, and the world would be a very different place. Let's begin by talking about the thing that physicists call a field. The need often arises to describe something that can have a different value at every point in space, like the air temperature, or like the wind velocity, or like the strength and direction of some force, such as the Earth's magnetic field. There are only 4 forces that we know of, and they are all described by fields that give their strength and direction at every point in space. But take note that a force field is something real. It is not just a number for every point in space. It has a physical reality. As John Archibald Wheeler said, it occupies space. It contains energy. Its presence eliminates the true vacuum. And in the words of Feynman, the field creates a condition in space. In classical physics, these fields were often thought of as continuous, smoothly changing entities. But quantum mechanics rejects the notion of continuous, and so fields become distributions of tiny field particles. And the strength of the field at any given point was nothing but the density or the quantity of field particles at that point. These particles are called virtual particles because they violate the conservation of energy rule for extremely short times in order to exist. They exist because of energy fluctuations allowed by Heisenberg's uncertainty principle, but they must disappear quickly because of the same principle. In force fields, like electric or magnetic fields, these field particles are called gauge bosons. They are the physical reality that occupies space as described by Wheeler. And while gauge bosons exist as virtual particles when generated in violation of conservation laws, they can exist as real particles too, if they are given enough energy to satisfy the conservation accounting. Most fields in science are generated by some source. An electric field is generated by an electric charge. Take away the source, and the value of the field goes to 0. And Feynman's condition in space disappears. But the Higgs field is different in this respect. It still has a value, a physical reality, at every point in space, even without a source to generate it. So there really is no empty space anywhere. The entire cosmos is saturated with Higgs field all the time, everywhere. And because of quantum mechanics, this means there has to be a field particle. Enter the Higgs boson. Virtual Higgs bosons are the quanta of the Higgs field, and they interact with all particles except the photon, the graviton, and the gluons. The interaction between the Higgs boson and each particle is directly related to the rest mass of that particle. Since the top quark has the highest rest mass, it also has the strongest interaction with the Higgs. The electron is 300,000 times less mass than the top quark, so its Higgs interaction is much smaller. And the almost massless neutrino has only a tiny interaction. Since the Higgs permeates all space, any particle that interacts with the Higgs interacts with it all the time and everywhere. The Higgs particle acts like sticky bits that put a drag on other particles, and it is this drag that we detect as rest mass. In order to detect a Higgs boson in the laboratory, we must create a real one instead of a virtual one. We do this by slamming particles and antiparticles together to create fireballs of terrific energy. And out of this fireball, we look for decay products that indicate that we created a Higgs boson. There may be as many as 5 Higgs fields, each with its own boson. And hopefully in the next year or so, we will discover how many and how massive they really are. Why is gravity so weak? Why can a small magnet pull or push something away from the entire Earth? There is an idea that may explain it. But before we go there, let's explore more preliminary ideas first. The most popular quantum gravity theory of today describes all fundamental particles as vibrating strings of energy. And the theory is constructed in a whopping 9 or 10 spatial dimensions instead of the 3 that we experience in our everyday lives. But what is a dimension? A line is a familiar geometric figure and can be completely described by giving its length. It is a one-dimensional object. It can be imagined that the dimensionality of an object can be created by taking an object of one less dimensions and moving it at a right angle to that dimension. You can create a line in your imagination by thinking of taking a point and moving it. Next, consider a surface. A surface is also quite familiar. A surface has both length and width and requires 2 measurements to define it, and therefore is a 2-dimensional object. Similar to a generation of a line from a point, we can generate a 2-dimensional surface by taking a line and moving it in a direction other than the direction of the length. And a solid figure is the stuff of everyday life. It has length and width and depth, and requires 3 measurements to describe it, and is a 3-dimensional object. And like the generation of a surface from a line, we can generate a 3-dimensional object like a cube by taking a square and moving it in a direction other than the direction of the length and the width. Cylinders, cubes, and spheres are 3-dimensional objects. And now the hard part. The higher dimensions are created by moving a 3-dimensional solid in a direction other than the length, width, or height. And while that is easy to do mathematically, it is impossible for us to picture it. So let's examine how we might detect these other dimensions. We begin with bright light spreading out in a spherical shell. The intensity of the light at any one point will fall off the square of the distance from the source, because the surface that the light covers grows as the square of the distance from the source. But that is only true in 3-dimensional space. In 4-dimensional space, the light will grow dimmer as the cube of the distance. And in 5 dimensions, it will grow dimmer as the 4th power of the distance. And in 10 dimensions, it will grow dimmer as the 9th power of the distance. Now back to strings. If this membrane represents the 3 dimensions that we live in, then particles like quarks and electrons are the strings that have the endpoints forever attached to those 3 dimensions. They might look like this. But the particle that is the force carrier for gravity, the graviton, is a closed loop. It has no ends that are constrained to our 3 dimensions. So if there are other dimensions, gravity will propagate freely there as well as in our familiar 3. And that might explain why gravity seems so weak to us. We experience only a tiny fraction of gravity's true strength because so much of it is leaking out into other dimensions. But where are these dimensions hiding? One possibility, but not the only one, is that they're all around us, but incredibly tiny. If you look at a wire or a string from far enough away, it looks like a line, a one-dimensional figure. But if you get closer, or if you were a lot smaller than the thickness of the wire, then you would easily see that it has other dimensions. On the tiniest of scales, space has extra dimensions at every point. It might look something like this if we were small enough to see it. Accelerators like the LHC at CERN smash protons together at enormous energies, perhaps enormous enough to produce gravitons. And if they do, then perhaps we might just be able to see them form in our limited three-dimensional world and slip quickly and quietly away into those hidden dimensions. The universe itself was created in an enormous explosion some 13.7 billion years ago. Before that explosion, there was no time, no space, no energy, and no matter.